Oh, hectic.
Oh no.
But that's okay.
Is it like a good hectic or like a...
Not really.
Oh no.
But that's okay. Yeah, I'm like scarfing my lunch like in the beginning of class.
Oh yeah, I see that.
On camera.
8051. You might be right,
All right, so I posted your first homework assignment, which is due on the 15th, which is a week from today. And it's 3 questions. So I'd like you to write these up neatly using those guidelines that I posted for writing up homework. The first question, I'm giving you 3 propositions. P is the proposition you have the flu, Q says you missed the final exam, and so on. And I'd like you to write down what each of these statements, A through F, says in English. In other words, the first one says if P, then Q. So it says if you have the flu, then you miss the final exam. Okay? And try to write down very literally what each of these expressions in propositional logic is saying in English. Don't translate them though. Okay? I mean, if it says, not you have the flu, you can say you do not have the flu. But don't combine them and simplify them into something else. Just very direct mapping from what's written here, right? If you have the flu and you miss the final exam, or et cetera, et cetera. And remember, these things are just conjunctions or disjunctions. This says P or Q or R. This says if P, then not R, or if Q, then not R, and so on. So just getting some practice using those. Second one, use truth tables to show that P if and only if Q is logically equivalent to that other expression. And we'll do an example of that shortly, where I show you a truth table to show that 2 things are logically equivalent. And then the third one is talking about things that we call quantifiers, and we have to talk about quantifiers still, but I'll ask you to tell me whether each of these statements is true or false, and if the first 2 are true, give me an example. If the second 2 are false, give me a counterexample. Yeah?
For the first question, you don't want us to box those answers, right? Because they're just sentences.
What do you mean by box them?
Circle them. Yeah, circle them.
If it's not clear what the answer is, circle it.
Okay.
But if it says, parentheses A, and you just write down what it is, that's pretty clear.
I'm not asking if I can print it in.
We don't need to print this out, right?
No, you can write it up.
Okay.
That's fine. If you really like printing things on a computer, that's okay, but generally it's a lot quicker to just write it by hand. So, and I'm fine with that. Okay, so let's play with truth tables a little. So here's a proposition. P or not Q implies P and Q. And since it's a proposition, we can write a truth table for it. And so you might see this on a homework question or a test where it says show a truth table for this. So let's systematically make this truth table. There's 2 variables here, P and Q, 2 propositions. So I'm going to make my table with 2 columns, one for P and one for Q, and I'm going to list all possible values of P and Q together. So both false, false, true, true, false are both true. And if you've done 250 with me, you know this trick I'm about to show you, which is break this down into little pieces. I want to write a truth table for this thing implies that thing, but I'm not just going to write that down directly, because that's a lot of work I have to do. I'm going to break it down into pieces. I need to write a truth table for P or not Q. Well, that means I need a truth table for not Q, so I'm going to make a new column here for the negation of Q. And filling that column in is really easy because it's just a complement of this Q column. So this is just true, false, true, false. And now I want a column for P or not Q. Well, that's just the logical OR of this column with this column. Well, I know how to OR two things together. If either one of those is true, the OR is true. If both of those are false, the OR is false. So there's the truth table for P or not Q. There's two advantages to doing it this systematic way. One, it's easier and less likely to make an error. And two, if you do make an error, I can tell where your error is. If you accidentally write an F here, but then everything else is correct based on that, I know you just made a typo here. It's not a big deal. Okay, well, I want to know if this column implies P and Q. I'm going to make a new column. I'm going to call it P and Q. And I know how to do an AND. I basically need both P and Q to be true. So here, here, and here, P and Q is false. But down here where P and Q are both true, P and Q is true. And now I want a column for P or not Q implies P and Q. So I want to know when this column implies that column. And I might make a little cheat sheet down here to remind me what the truth table is for implication. So what's the rule for implication? When is A implies B true? Or when is it false?
When they're both true or false.
Say again?
When they're both true or false.
When they're both true or false, it is true, right? And there's one other case where it's true. This gives me a chance to eat.
If the hypothesis is false, then it's always true.
If the hypothesis is false, it doesn't matter what the conclusion is, the implication is always true. And that leaves us one case where the implication is false. And it's precisely when the hypothesis is true, but the conclusion fails to be true. Okay, well, to fill in this column, I basically want to look at these two columns. And if this first column is is true and the hypothesis is false, hypothesis true, conclusion false, the implication is false. So those two are false, and these two are true. So there's a truth table for that expression that I wrote on the top. What, does this truth table look familiar? A little bit? What's it look like? It looks exactly like Q. Regardless of the values of P and Q, this expression always has the same value as the value of Q. So by writing this truth table, we've actually proven a theorem. We've shown that this expression is logically equivalent to Q. Now, if you'd been given a question on a test which said, prove that this expression is logically equivalent to Q, this would be one way to do it. Write a truth table, figure out what the truth table for this expression is, and then just make the observation, these truth values are identical to the truth values for Q, therefore those two expressions are logically equivalent.
What would a biconditional truth table look like?
Biconditional We've got our cheat sheet here for A implies B. So B implies A. Let me just do it on a clean sheet. So this is always true except when the hypothesis is true and the conclusion is false. B implies A is always true except when the hypothesis B is true and the conclusion A is false. So this is true everywhere else. So the biconditional is just the conjunction of A implies B with B implies A. So it's just the AND of these two columns. And it looks like that. And so bijunction is really just an exclusive NOR, which might make you feel good or feel kind of funny. And so this is engineering 250, right? We proved statements about Boolean expressions by using truth tables, and it looks very much like the same procedure. So let's play a little more with this idea of propositional equivalence. The idea that this is equivalent to an exclusive NOR, or that this expression was equivalent to just the expression Q. There's two propositional equivalences that we're very interested in. One is called a tautology. So a tautology is a proposition equivalent to true.
How do you spell that?
Tautology, but I wrote it a little sloppy because I'm not sure.
Okay.
I think it's tautology. Ology. A contradiction is a proposition equivalent to false. So an example of a tautology, a proposition that's logically equivalent to true, P or not P. Whatever the value of P is, either P is true or the negation of P is true. And if I write the truth table for P or not P, every row will have a T in it. So it's logically equivalent to true. Good example of a contradiction, P and not P. That's always going to be false. Because I'm basically saying P is true and also not P is true. Or I'm saying P is true and P is also false. All right, there's our truth table for implication, if then. If I write a column for the negation of P, that's going to be true, true, false, false. And now if I do, that should be a negation symbol, negation of P. So now if I do negation of P or Q, I'm looking at Q, I'm looking at not P, and I'm doing a logical OR between those, a disjunction. This is true, true, false, true. And this always has the same truth value as that. True, true, false, true. So we can now make the following statement. If P, then Q is logically equivalent to negation of P ORed with Q. And this is a theorem that we'll use a lot. It's a theorem called conditional equivalence. And it tells us anytime we have this, we could use that instead, or vice versa. All right, so we can start writing identities, equivalences between expressions. And there's a number of these. We'll talk about a few of them. P ANDed with true is logically equivalent to what? Well, let's pick a proposition. P is the proposition that today is Wednesday. So this statement says today is Wednesday and true.
Not false.
Say again?
Not false.
Not false, but if P was the proposition today is Monday, then today is Monday and true would be false. So this could be true, it could be false, but it's equivalent to something simpler than this. It's just equivalent to P. Saying, you know, this statement is true and true is true is exactly the same truth value as just saying this statement is true. And similarly, P or false is logically equivalent to just P. So for example, let P be the proposition I am eating lunch, which I am. Right? This is saying I am eating lunch and 1 plus 1 equals 2. That has the same truth value as simply I am eating lunch. If I'm eating lunch, then I'm eating lunch and 1 plus 1 equals true is true. If I'm not eating lunch, the statement I'm eating lunch and 1 plus 1 equals 2 is false. Right? It's exactly the same as the truth value of P. And in the disjunctive case, I am eating lunch or 1 plus 1 equals a million. Well, the truth value of that is the same as the truth value of just I'm eating lunch, because 1 plus 1 is not a million. All right, so when you OR something with false, it's the same as just the thing you're ORing. So those are identities. Those are actually called the identity. What about P ANDed with false? I'm eating lunch and 1 plus 1 equals 1,000,000. What's the truth value of that? I'm eating lunch and 1 plus 1 equals 1,000,000.
False.
That's absolutely false. Doesn't matter if I'm eating lunch or not. Because this says P is true, and it says, this thing that's false is true. Well, it's not true, it's false. So the and has got to be false. And P ORed with T. So I am the Queen of England, or 1 plus 1 equals 2. What's the truth value of that statement?
True.
It's true because this second part was true, and we only need one of these things to be true for the OR to be true. It doesn't matter what the value of P is. P can be completely false, but since I'm ORing it with something that's true, the result of this is true. So this is a property called domination. P or P is logically equivalent to P, which is logically equivalent to P ANDed with P. That's a property called idempotence. Negation of the negation of P is logically equivalent to P. That's double negation. And we already talked on Monday about commutivity. And we talked about changing the parentheses around.
Is that word that starts with 9?
What's the one?
The word that starts with 9?
Which row? Idempotence? Yeah.
Which one is that?
That's this. And these are in your book. They should be on page 57. But let's see.
Yes, sir.
58. So they're in your text, chapter 3. Commutativity, associativity, distributive, identity laws, negation laws, which I called something else. And there's other ones, and we talked about De Morgans on Monday also, right? So there's all these properties, all these theorems that we have access to about putting propositions together. And one thing we can do with these is we can use them to prove theorems, more complex theorems. And this is more 250 stuff, right? If you just replace an and with, a dot and an or with a plus sign, these are all things from the Engineering 250 course. Right? The idea that if you take something and you or it with 0, you get the thing back. If you OR it with 1, you get a 1. They actually use 1s and 0s instead of T and F here. So that's Boolean logic, right? That's what 250 is. So let's do an example. we want to prove that these two expressions are logically equivalent. Now, we already said we can do this with a truth table, but I want to do this without using a truth table. We only have 2 variables. A truth table would only have 4 rows. But if we had 10 variables, our truth table would have 1,024 rows, and that's a lot of work. And sometimes it's easier to use these identities to prove things by modifying these expressions into equivalent things. So we're going to spend a lot of time doing proofs in this course. This is probably our first full-on proof. When we're trying to show that 2 things are equivalent to each other, really the only way that we're allowed to do that is to start with this first thing, use identities that we believe, meaning they're on page 58 of our textbook, to modify this until it looks like that. Or we could start with this and modify it until it looks like that. Both of those are perfectly fine ways to prove. Here's what we cannot do, but a number of us will be tempted to do. Take some identities and do some stuff to this left side, and take some other identities and do some stuff to this right side, and then show that the 2 things we ended up with were equivalent to each other. That is not a valid proof method. And I'll give you a really silly example of why that's not valid. But the silly examples are easy to avoid. It's the more subtle ones that are easy to fall into. But here's an example. Prove that 3 is equal to 4. Well, if I can start with 3 and I can do something to it that makes it equivalent, like multiply it by 1, or add 5 and subtract 5, right? That's totally valid. And if by doing these things I end up with 4, I've proven 3 equals 4. Okay? Here's what's not valid. What did I do? I took both sides and I multiplied by 0, and that led me to state that 0 equals 0. And in fact, this is true. 0 does equal 0. So yeah, 3 equals 4. I'm done with my homework. I'm going to go do something else. It's not a valid proof. And it's really obvious here that this is not proving that 3 equals 4, right? But this is exactly what a number of people will be tempted to do in the middle of these propositional logic proofs. And it's really easy to do this without realizing that's what you're doing. Okay? So you can never start with something and do the same thing to both sides and get an equivalency and then say, okay, so therefore this was originally equal to that. It's not a valid, it's not a logical way to prove this. Okay, so we'll bump into this a lot, and I'll say more about it in other forums down the road, but just kind of keep in your mind, sometimes I'm going to say that you've done this, okay, but it will be more subtle than that. So we can't start doing things to both sides, but we can start with one side and we can modify it using these kinds of logical laws. Okay, well, let me just rewrite the left side. And I want to show it's logically equivalent to something else, hopefully something simpler, because I'm trying to get it into a really simple form. So we've got the negation of the quantity P or this other expression, not P and Q. And we want to change that into something else. Is there anything up here that we might use to somehow simplify this expression? Negation of P or the quantity, negation P and Q. Any of these laws that might apply? De Morgans Theorem. Right? De Morgans Theorem says if we have a negation of 2 things that are ORed together, we can change that into something else. We can split up that negation. Well, here we definitely have a negation of something ORed with something. Now this is game playing, right? there's nothing that tells us absolutely that this is a good thing to do. It might be that we really want to use this commutative law and switch around the order of these two things. Maybe when we do that, magically things will get simpler. We really don't know. It's a trial and error, okay? So it's game playing. It's looking at these things and trying them. And the more you do this, the better your intuition becomes.
I could see this being a thing that I might do, and I want to know if it's valid. Can you do like distributive property on the negative and then like?
Yes.
that out? You
So
can?
we could distribute the P across the not P and the Q.
Okay.
And that might be another good pathway to an answer.
Oh wait, you're talking about doing the P?
Distributing this over these two, you mean?
Yeah. So I was talking about the not sign.
Not signs don't distribute unless you change this thing to an and. That's what Morgans Theorem basically says. So let's do De Morgan's. So this says that, so De Morgan's theorem strictly says negation of parentheses P or Q is the same as the negation of P ANDed with the negation of Q. So the negation of this ORed with that would be the negation of P ANDed with the negation of negation P and Q. And the reason for that is De Morgan's theorem.
One too many parentheses.
That's very possible. There's my big parentheses. All right, what can we do on that right-hand side to make it into something else?
Do De Morgan again. On the right side.
We could do De Morgan on the right-hand side. So I'm going to leave this first term, this negation of P, alone. And negation of something ANDed with something, De Morgan part 2 says that's the negation of the two things ORed together. So this is logically equivalent to the negation of P ORed with the negation of Q. And that's also De Morgan's theorem. Now, I'm going to be long and wordy one time, and then we're going to get a little sloppy. But right now, I am rewriting this right-hand side and saying it's equivalent to something. But that's twice as much ink as we need to spend, so eventually we'll just keep saying this is equivalent to that, is equivalent to this, is equivalent to the other thing. But the first time through, let me do it the long, wordy way. What can we do to simplify this expression?
The double negation.
A double negation. Double negation says not P is equivalent to P. It's called the involution law here, but it's really just double negation. So that's double negation. All right, what can we do with this one? It's something ANDed with something ORed with something.
You could use absorption loss.
So P ANDed with P or Q, or P ORed with P and Q.
Right, so that wouldn't work.
But that doesn't work because
Yeah.
we have a not
Yeah.
P and then a P and a not Q. But there is something we can use here.
Can you distribute?
We can use distribution. So distribution says something ANDed with an OR is equivalent to that something ANDed with the first part of the OR, ORed with that something ANDed with the second part of the OR. And I'm just doing this very sort of rigorously. I'm not really thinking about what it means. Distribution says this is equivalent to the first thing ANDed with this piece, all of that ORed with this first thing, ANDed with the second piece. And that's distribution. Change my parentheses a little bit here. All right, what can we do to this?
It's a law of non-contradiction on the left. right?
Not
Just
P
false.
and P. We have a law about that. So we're told P and not P is equivalent to false. Now technically, and again I'm going to be really, really long and wordy about it this time, technically the negation law does not apply to this expression on the left, because the expression on the left is not P ANDed with P. The negation law says P ANDed with not P. That's a slightly different form. But I can say that this is equivalent to P ANDed with not P, ORed with not P ANDed with not Q. How did I get from this to that? Do you remember the name of that?
It's on the page.
Is that commutative?
That's commutativity, yes. So commutativity, you can switch the order around. So that's commutativity. And now,
So we can never go 2 steps at a time. We would have to always.
I'm going to let you do steps at a time in the future.
Okay. So that's not.
But I'm just being really, really wordy here. I want you to see actually everything that's taking place. But in practice, right, if you want to take this and just say that's equivalent to false, I'm going to be okay with that. But I'll do it the absolute fullest way first, and then we'll take some shortcuts. Okay, so now I have P ANDed with not P, and that's exactly the setup of the negation law. P ANDed with not P is equivalent to false. So now I can say this is equivalent to false ORed with not P and not Q. And that is negation law. Okay, what can I do with false ORed with something?
Identity.
Identity, except again the identity is saying something ORed with false. So let's do one more commutativity law. If we're paid per line of proof, this is good practice. That's commutativity again. All right, now we can say identity law says something ORed with false is just equivalent to the original something. And that's, yeah, identity law. So I did an extra commutativity step here to switch around the false to the right side, and then the identity law applied and said that was equivalent to that. So what have we shown? We've shown that our original expression here on the left was equivalent to something, which was equivalent to this, equivalent to that, and this, and this, and this, and this, and ultimately equivalent to that, which is what we were trying to show. Okay, there's a fancy way to write which is what we were trying to show, and that's to write QED. QED is Latin for which is what we were trying to show. And it basically tells the person reading your proof after they've fallen asleep 5 times going through all of this, wake up, here's the thing that I was asked to show. Okay, then they can say, okay, you're right, that's equivalent. Yes?
So I'm assuming you'd really only want to do this when the expression's like too big for a truth table.
Or if I say, do it like this. But yeah, in practice, truth table is pretty straightforward. And if you have a computer, truth table will chow on this really, really quickly. All right, so what's a more realistic way of doing this? Right, so we would start with that. We would use De Morgan's theorem to get down to this. And then I would just say this is equivalent to not P ANDed with not P or not Q. That's De Morgan's theorem. And then I would say this is equivalent to not P ANDed with P or not Q. And that's double negation. And I would say that's equivalent, and I would go ahead and distribute not P and P, or not P and not Q. And then I would go ahead and I would say, well, not P ANDed with P, that's false, or not P and not Q. And that's whatever we call that negation law. And false ORed with something is just equal to that something. Not P, not Q. That's the identity law. And that's what we were asked to show. So this would be a perfectly acceptable proof. Okay? The difference is I didn't keep writing the right-hand side down here on the left. This is, if this was on a piece of paper, it would just be one big long line. This is equivalent to that, equivalent to the next thing, and so on. I'm just breaking it into lines here. And I'm not worrying about the fact that technically on page 58, my negation law says P and not P, right? Because I could modify my text, and I could write down in here, yeah, not P and P is also equivalent to 0. And I could write here, 0 ORed with P is also equivalent to P. Right? So those sorts of, having to switch around the order to match what's in the book, those you can skip. But I would not go directly from here to there, right? I would want to see a step that actually says not P and P got replaced with false. And then false ORed with something got replaced with that. Why? Because you had to do 2 things to get from here to here. You had to use the negation law and the identity law. And those are non-obvious enough that you want to make sure they're separate steps. So you can't go wrong by having too many steps. But if if you're really, really intuitive about this stuff, you might look at this and in your head you say, oh yeah, this is equivalent to that, QED, right? But you got to write down all the steps. The way to think about this is you're taking this proof and you're showing it to somebody who understands Boolean logic but isn't necessarily like, an Einstein about it. And you're trying to convince them that this is equivalent to that. Well, they know what De Morgan's theorem is, so if you state this, they can look at De Morgan's theorem and say, yeah, that's true, this is equivalent to that. And now you say this is equivalent to that because of De Morgan's theorem, and they can look at De Morgan's theorem and say, oh yeah, I can see that. But if you suddenly jump from here to this is equivalent to this, they might not know how you got there, right? So the idea of a proof is to demonstrate to somebody how you got from this original thing to this final thing, and you're demonstrating each step along the way to convince them.
So the last bit that you got is equivalent to the top left, right?
Say again?
The QED.
Mm-hmm.
That, or no, the
So
QED before that.
This?
Yeah.
Yeah.
That is equivalent to the top left.
Yeah, so basically we showed that this was equivalent to this, equivalent to that, and this.
Okay, and you're starting with that statement up there that the left and the right are both equivalent, and then you're trying to prove that the left is equivalent to the...
Yeah, I mean, I stated this was equivalent to that because of De Morgan's theorem, and that this was equivalent to that because of De Morgan's, and that's equivalent to that because of double negation, and so on. And so in the end, that's equivalent to that.
Gotcha.
All right, yeah.
Do we need to always cite the theorem that we use?
Yeah, I definitely want a reason on every line. And sometimes the reason will be something like algebra, or this is how integers work, or something like that. But you want to have some reason, right? And if it's totally obvious, just state what the totally obvious reason is anyway. And so think about this like going into a court of law and trying to convince a jury that this is equivalent to that, right? And they understand these theorems, but they don't understand that this is equivalent to that. You have to show them. Yeah?
Do we have to memorize every theorem's name?
No. So I will give you probably Friday handout that has all of these theorems on them and the even better theorems that come on the following page, which are these implications, because they have cooler names like conjunctive simplification and things like that. So I'll give you a sheet of those, and those do not count against your 8-page note budget for exams. You can always bring these with you and use them. So you can look them up. Okay, other questions about this? All right, let's take a 5-minute break. I'll finish my pizza, and then we'll talk about quantifiers. But stretch your legs for like 5 minutes. What?
Where'd you get the pizza from?
That's from the Rock.
Oh, nice.
Yeah.
What kind of pizza is it?
Plain cheese, man. Because Rock pizza is good enough to do plain cheese. That's my opinion.
I think Little Caesars is good enough for plain cheese.
I like Little Caesars.
I got it.
I won't admit that on camera.
Have you tried the buckets from the Rock?
No, I've seen people with those.
Those are good.
Yeah.
I'd like to see you get back to what it afterward. I think that. Yep.
Maybe put it you use them like fairly inconclusively.
Imagine doing the homework for 270 and a 250
Imagine doing the
Link to what you Yeah, just put it I don't know if that'll make a difference.
It says underground.
It's on main. You're not. Is that you call it a main function? Okay. That's how you're fine. What was it saying? The issue was?
You ask from your main fellow. Am I calm right?
Nope. It's up in there, right? Main.
Oh my gosh.
Yes. Main 202. Yeah, main 202. It doesn't matter what that's called.
Oh, cool.
Run it. Run main 202. Yeah, just run main 202.
Just main 202.
Yep. It repeats what you typed. That is not correct. You did. What it should do Yeah, are you including 100? I is less than or equal to 99.
Oh.
You go do the same thing. I think I did less than or equal to 100, or less than 100.
Why?
Or compile it again. Can you do that?
Yeah. Oh, wait, that's right. I'll look.
Or 291 1? Is it running 3 times? It should be.
Did that sign-in sheet make it around the room?
What did you just say? I got it.
Did you do one for 222 earlier?
Not really. I did one for A and I didn't do it for B, so.
Okay, I didn't say it. for
That's
B.
okay.
Okay.
All right, we're going to talk about what are called quantifiers. And quantifiers relate to what we can think of as a family or a collection of propositions. So let P of X be a family of propositions, where X is some kind of variable, some kind of placeholder. And we need to know what the possible values of X are. For example, P of X could be a proposition about students in this class. And X could take on the identity of any student in this class. And P of X might be the proposition that student X is sitting in one of the first 2 rows. And for any value of X, any student in the class, that proposition would be true or false. Or we could say that X is an integer, and for example, let P of X be the proposition X is bigger than 5. And I'm going to specify in here where X is an integer. So depending on the particular value of X, each proposition P of X could be true, could be false. And this one symbol, P parentheses X, represents, in this case, an infinite number of propositions. P of 1 is the proposition that 1 is bigger than 5. P of 10 is the proposition that 10 is bigger than 5. And if X can be any integer value, I've got an infinite number of propositions here. Well, when we're working with these families of propositions, we have certain types of things we can say about them. So the first thing is what we call a universal quantifier. And the universal quantifier is written as an upside down A, followed by the name of a variable. And we can translate this as saying for all X. And so I could write the statement for all X, P of X. And this is a proposition. It's the proposition that for all possible values of X, the proposition P of X is true. So P of X is a family of propositions. For all X, P of X is a new proposition. It's making a statement about this family, this collection. And if P of X was the proposition X is bigger than 5, is it true that for all X, X is bigger than 5? That's not true, because X could be equal to 2. which is not bigger than 5. So this proposition has a value of false, assuming that x is an integer. Now, if I said for all x, where x is a 3-digit prime number, then yeah, it's true that for all such x, x is bigger than 5. Because 3-digit prime numbers start with 101 and go up, and those are all bigger than 5. So this sort of universe over which x can vary is critical to the truth value of this. And so for some examples of this, we might say for all x, x is less than 0, or x is equal to the absolute value of x. And I'm just going to write down over here, x is an integer. But you always need to be told what the set of possible x's are. Okay, so for x an integer. For all x, x is less than 0, or x equals absolute value of x. Is that true or false? That's absolutely true, because if x is less than 0, this part is true, and so the entire disjunction is true. If x is bigger than or equal to 0, we know that x is equal to its absolute value. And so this right-hand side would be true. And so in all cases, either the left or right-hand side is true. And so this statement that for all x this is true, that's absolutely true. For all x, x squared is bigger than or equal to 0. Is that true or not true?
It's true.
That's true, assuming that x is an integer or a real number. But if x was taken over the space of complex numbers, where it could be, say, the square root of -1, then x squared would be -1. That's not bigger than 0. So again, the universe matters. But for these, I'm just going to work over integers. Most of this course we deal with integers. Occasionally we'll talk about reals.
Can discrete deal with floats, or is that?
Yeah.
Oh, they actually can.
Oh yeah, it's a pretty critical subject. Partially as a counterpose in some ways. But yeah, it's all related. Even though they're not discrete, right? They're continuous. All right, here's a highly symbolic one. For all x and y, x squared equals y squared implies x equals y. Is that true or false? Again, working over integers.
It's false.
That's false. Why?
Negative.
Because you could have x be -1 and y be +1. X squared equals y squared, but x is not equal to y. But if x was a positive integer, then this would be true. All right, so you got the idea? All right, so that's a universal quantifier. There's also the existential quantifier, which we write as a backwards e, followed by the name of a variable, and we can read this as there exists an x such that. So there exists an x. The universal quantifier says for all x, the following statement is true. Existential quantifier says there exists an x for which this is true. So there exists an x such that x squared equals x. Is that true? Go ahead, question.
I was just going to ask, when you say there exists an X, does that mean specifically one?
No.
Okay.
At least one.
At least one, all right, thank you.
Yeah. So there exists at least one X for which X squared equals X. Is that true? Yeah. What's an example? Yeah, 1. Is there another example?
0.
0. So this is definitely true. There exists an X such that X is bigger than X squared. Is that true? If yes, what's an example? So if there's a fraction, yeah. If we go over the integers, it's false. If we go over reals, we could do 1/2. And 1/2 is bigger than 1/4, which is its square. So this is false if X is an integer. It's true if X is real or even just rational.
And is that something that we would have to say while we are deciding whether it's true?
So when you're given a problem like this, you should always be told what the possible legal values for X are. If you're not and it's not clear, you definitely want to ask, especially during a test,
Gotcha.
right? Because sometimes it makes a difference and one forgets.
And the way to symbolically write if X is an integer would be X and then the subset symbol.
So we'll get into this in a few weeks, but we can say X, we can say contained in, and then there's a symbol for the integers, which is this funny looking Z. But we don't get to that till we talk about set theory, so I'll probably just say where X is an integer. But yeah, that's where we're hitting. All right, so there exists an X such that X squared equals 9. Yeah, X could be 3, X could be -3. So that's definitely true. There exists an X such that X squared equals 2. Well, over the integers, that's false. And in fact, over the rational numbers, the fractions, that's also false. There's no fraction whose square is equal to 2. The Greeks knew that. But over the reals, this is true. It's just a number called the square root of 2, 1.414, etc. So over integers, we'll say false. All right, we do have a symbol, though. E exclamation mark, which means there exists uniquely. So if we do an E with an exclamation mark, that means there is exactly one X, for example, for which this is true. So we can specify uniqueness. Yeah?
Is there other versions for there's like different quantities of exact amount? Like there's exactly 3 values?
I haven't seen one. There probably is. There's probably a whole science around that. But I haven't seen it. It's probably a really interesting question. Like, what's the nature of statements for which there are exactly 2 things that satisfy it? All right, so back to this idea of a family of propositions. Right, and the proposition P of X would be, you know, the proposition that X is bigger than X squared, the proposition that X squared equals 9. Right, it's a collection of propositions. You plug in a value of X, you get a new proposition. P of 2 would be the proposition that 2 squared is equal to 9. Right, so keep in mind, even though we're writing down statements here, we can think of these as families of propositions. Okay, so for all X, P of X. What might we get if we negate this proposition? So the proposition in parentheses says for all X, P of X is true. What's the negation of that statement? Just in kind of like plain.
Existential quantifier, right? If
Yeah.
There exists an X,
There exists an X such that what?
it isn't true.
Such that it isn't true. The opposite of saying for all X, P is true is for some x, p is false. Right? For every student in here, you're in class today. Right? For every student in 215, that student is in class today. Well, the opposite of that is there is at least one student who is not in class today. So this is really equivalent to there exists at least one x such that not p of x. And we can go in the other direction. The negation of there is an x such that p is true, while the opposite of that is for all x, p is false, or not p is true. So we've got some equivalencies, and they almost look a little De Morgan-ish. By moving the negation, we change our symbol from an A to an E or an E to an A. That's kind of the feeling of De Morgan, right? When you distribute your negation, you change from an and to an or, vice versa. So there's something going on there. Okay, let's talk about natural numbers. And there's not a universal agreement what natural numbers are. Different textbooks will do different things. They always include the integers like 1, 2, 3, 4, and so on. And sometimes they also include 0, sometimes not. But they never include the negatives. So I think in our text the naturals include 0. If I ask you something about the naturals, I'll try to specify exactly what numbers I mean, and if it's not clear, ask. But for now, let's just suppose naturals start from 0. And what is a natural number? I mean, that's a funny term, isn't it? Natural, unnatural. What's unnatural about negative numbers? They don't really exist in the real world. You can have 2 cows, you can have 5 cows. Maybe you can have 0 cows, but you don't have to milk your cows if you have 0 cows. But what does it mean to have negative 3 cows?
Somebody owes you 3 cows.
Yeah, but that's a relationship with somebody else, right? I mean, do I keep my negative 3 cows in a negative barn? Do I have to feed them negative hay? I mean, it's a weird concept. It's not natural in some sense.
Dead cows.
Yeah. And you know, for a long time, people did not deal with negative numbers. People did not deal with 0 for a long time. Because the idea of having 0 ounces of gold, you know, yeah, I have a lot of gold. I have 0 ounces of gold, you know. I have 0 ounces of magic pixie dust. Well, you don't really have any magic pixie dust in your hand, do you? I do. I have 0 ounces of it, you know. It's a fundamentally different concept from something bigger than 0. And negatives are just even weirder, right? So for a long time, nobody dealt with negative numbers. So natural numbers are the ones that kind of occur in nature. We don't find negative cows in nature, but we can use the concept of a negative cow when we're bartering, you know. I'll give you, you know, some shoes and you'll owe me some cows, you know. And fractions are the same way. The idea of half a cow is weird. Or the idea of owning a quarter of a house. It's like, which quarter do you own, you know? Those don't make sense in some natural way, but we can use the idea of fractions to do lots of useful things. Like, you know, if you own 2 1/4 cows, and if 2 1/4 cows are worth this pair of shoes, and I give you 10 shoes, how many cows do you give me? Right? Well, we can do the math. But these things, when they were first introduced, were weird. Zeros and negatives and fractions. And I'll show you a more modern example. Right, what's the solution of this simple equation, x squared equals minus 1? What's the value of x that solves it? Why is it I? What does I stand for?
Or -1. Imagine.
It's imaginary, right? We call these things imaginary numbers. That's like calling it unnatural, you know, or irrational. Square root of 2 is called an irrational number. Same thing, we don't encounter square root of -1 of anything in nature. Well, we do in physics, but, you know, how many cars are in the parking lot right now? Oh, square root of -1. It doesn't pop up that way, right? And it doesn't map to anything in our daily experience, so we call them imaginary. But they're really, you know, they make perfect sense as an abstraction. So we'll bump into that occasionally. So let's look at natural numbers. And we have a symbol for the natural numbers. It's this funny looking n with a double bar on the side. So for all x, where x is a natural number, p of x. For all natural numbers x, p of x is true. We can write an equivalent statement to this. What does this mean? It means that if x is equal to 0, p of x must be true. Agreed? Since 0 is a natural number, and this says for all natural numbers p of x is true, p of 0 must be true. Well, if x is equal to 1, that's also a natural number, and for all natural numbers, p of x is true. So if x is 1, p of 1 must be true. So not only is p of 0 true, but p of 1 is also true. And p of 2 is also true, and p of 3, and so on. So this is really a shorthand notation of writing p of 0 and p of 1 and p of 2 and ... It's saying that the and of all of those, the conjunction of all of those is true. And what about there exists an x such that p of x, what's that equivalent to? That says either p of 0 is true or p of 1 or p of 2 or something. And assuming I write this out for all possible values of x, it's saying that at least one of those must be true, and so the disjunction of all of them, the or of all of them, must also be true. And so these are exactly the same statement as each other. So this is really just a shorthand for these really long expressions of ands and ors. But this is going to be a really critical notion for something we're leading into in a couple of weeks called mathematical induction, the central theme of this course. And it's really about proving things about a family of propositions over the natural numbers. And we'll see lots of ways to do that and lots of good things that come out of it. All right, that should give you enough to do the homework. Okay, so my suggestion is work on the homework and bring questions on Friday. Okay, if something's not clear what it's asking for or some concept we went over isn't working for that, we can talk about it on Friday. We'll go on, we'll talk more about logical equivalence, nested quantifiers, and then we'll start talking about rules of inference. This is where we get into full-blown mathematical proofs. All right, so I'll see you on probably tomorrow in class.